Okay, so we should be streaming now. Yeah, it'll be easy to take that survey. Trust me, I think I took it. It's 2-minute survey. I think it's 8 questions. Super easy. All right. Okay. Whoa, we don't want to start there. What page did I say? 117, I think.
Yes.
All right. So universal gravitation. You have 2 objects. Okay. And let's say they're just objects 1 and 2. They're 2 masses and they're separated by a small distance. This equation right here is the way we could calculate the force between any 2 objects that have mass. This is not just planet Earth and a box. This could be my foot and a bucket. It could be Mars and Jupiter. It could be the sun and our moon. It could be a satellite and our moon, or a satellite and our Earth, or the moon and our Earth. Basically, any 2 objects have a gravitational force between them. Now, this force, there's a constant. Great. All right. But notice it depends on 1 over r squared. This is called an inverse square law. Basically, the force depends on the inverse of the distance between the 2 objects. And then the direction here, we've got to look carefully. So I just want to point out this way is R1 to 2. I'm going from 1 to 2. This right there is a unit vector in that same direction. And the net force ends up being opposite the direction of that. So 1 exerts a force on 2 towards 1. Another way to say that is in the negative 1 to 2 hat. So, all right. Now, that's another way of saying mass 1 attracts mass 2. And you may be saying, this is a dumb way to write it. At first, I might even be inclined to agree with you until we see a few example problems and do a little bit of work. And you're like, wait a minute, this actually can be kind of useful. I'll show you why in just a second. Now, to be clear here, the distance between them is called the center to center distance. So notice in that picture, I'm not going from the surface. I'm going from the center of this one to the center of that one. That's the vector that we want to use, from the center to the center. All right. Now, there's a cool trick we can use. Oh, and this is going to be the gravitational potential energy. We'll cover that more in a minute. Well, let me show you something right here. A lot of times we actually end up writing this a totally different way. Now, I don't know if you know this, but maybe you remember it from chapter 3. R1 to 2 hat is actually equal to this junk right here. As a result, we can rewrite this in another way. Vector over R1 to 2 magnitude to what power? What power would I need to use on the basement now? If I use the whole vector up top instead of the hat. Right? I could rewrite R hat as the vector over this. So what power should I have in the basement? Three, because I had squared here plus another one from there. All right. Now, you might be saying, this is strange. Okay, fine, whatever. Let me show you something. Just what you didn't want to see. Let's take a look here at this one. Okay, now just bear with me. All right. This is a boring coordinate system. This is a constant. This is just used to scale the arrows to make them bigger or smaller. I'm going to have an orange rock, and I'm going to have a blue rock, a cyan rock, excuse me. And let's put one of them at the origin, and let's put the other one at position 5. Let's just say it's position 3. How about that? Okay. Now, these are the masses, 8 million and 2 million, but they're only separated by 3 meters. So this is pretty absurd, but whatever. They're neutron stars or something, very dense. Okay. Look at this vector here, R1 to 2. Again, I'm going to show you this. So let's say here, rock 1 is orange, and it's at the origin. Rock 1 is orange, and it's at the origin here. Okay. Rock 2 is cyan, and it's sitting over here 3 units. That's 3 units over, right? So now take a look. If I go from 1 to 2, this is initial and this is final. So that's going this way. R1 to 2 vector. Okay. Now, look at this code right here. Rather than use r hat over r squared, I'm going to write it this way. Now, I'm going to just actually erase a little bit here and lower this down. What you could say is, why don't you just write this like this? Force of 1 on 2 is equal to G times the masses, all right, times the hat vector, times negative hat of R1. Give me just a second. I want to see that. There we go. R1 to 2 divided by the magnitude of R1 to 2. I could do it that way, right? And you could debate whether you want to have these parentheses or not, right? We wouldn't actually need these extra parentheses here, but yeah, I guess I was just leaving it on just so you could see that that's all the basement, right? It's just for cosmetics right there. I could do this calculation in either of these 2 ways, but I hope you agree the second one uses one more function call, right? We have to use 2 functions. So that's going to be slightly slower if we have to do it in the loop. So let me just get this out of here because we don't need it. Don't need that. Let's just do this just in case it locked up on me. I just copied everything and hitting reload. Ah, the joys of GlowScript. Yep. So let's just get rid of this junk. And let's run this thing and see what it looks like. Now, in this case, here what we see is, that's great. I've got this arrow, and notice the force arrow is really large because these masses are huge and they're only a little bit apart. But even then, you still only get 120 newtons from 2. These are millions of kilograms, okay? One of the masses was 8 million kilograms. The other was 2 million kilograms. They're only 3 meters apart, and the force is still extremely weak, only 120 newtons. This gives you a little bit of an idea of how weak this is. Now, you see this little comment here, sat level reached? I'll explain that in the code in just a second, and here I calculated the gravitational energy as well. Let's go back in and look at this one. What should happen to the force if I double this distance out here to 6? What should happen to the size of the force?
It should go down.
By what factor? I double the distance. Should it cut the
Okay.
force in half or what?
No, more to the fourth, I think.
It will divide it by a factor of 4. You're
Oh,
right.
but yeah.
So it was about
But
120 before, and notice now it's about 30. Right? So we see this is a property of the inverse square law. So good job, Gonzalo. If you double the distance, the force just doesn't get cut in half. It drops by a factor of 4, right? And so maybe we could do this just to make it a little bit prettier. We could just make these each 2. All right. So if I drop one of the masses by a factor of 4, that's just going to drop the force by a factor of 4, just like we thought. But now what you could do is you could see the arrows a little bit better here, right? So in this case, if I bring it twice as close, we'd expect the force to be 28. So now if I bring it back to 3, we should get back to 28. Okay, 29, whatever, same thing. All right, so that's a rounding error. That's my bad. All right, so now you might be wondering what this saturation level is. See how it says sat level reached? Let me comment on that. Here's the deal. Let me just a second. Get this cleaned up. All right. So now when I scroll down, here's the problem that we face. When you're drawing the arrows, right? Look at this little bit of code right here. It says if the size of the arrow is bigger than some arbitrary number, which I called the saturation level, then what I'm going to do is I'm going to draw the force at that size in the direction the force should be. So it draws, this is the direction of the force, and this becomes the size of the arrow, even though the arrow does not correctly represent the force. Why do we need this code? Why are these forces going to blow up and get huge sometimes? Mathematically speaking, why do the forces sometimes get large in this equation right here?
When they get really close to each other, it gets
Yes,
closer to 0.
because the force magnitude, if R gets close to 0, the magnitude of the force blows up. And so this becomes an issue. If you want to have your code run and the two masses are right on top of each other, it's not going to work. Now, let me ask you another question here. Oh, let me go back and see if there's anything else here. So that's the force. This, in comparison, computing the energy is really easy. Notice a couple of things. The force either has R vector over R cubed or R hat over R squared, whereas the energy just has one radius on the bottom. I will explain how we get that formula probably on Wednesday. That said, this calculation is really easy. The two things people forget, sometimes they forget the minus sign, and sometimes they forget that this is to the first power when force is to the second power. That's the main thing. So nothing crazy here. It's just stick in some numbers and compute it. Again, I'll derive how we get this formula later. All right, so nothing crazy there. But look at this. What if we wanted to make this thing move? Whoops. How about, let's do this one. So in this one, what am I going to do? I do a loop to make it move. I get the forces in there, the momentums, and draw the arrows and do this stuff in here. Okay, so blah, 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 a bunch of, okay. There's other stuff we could do here, but let's just run this program and see what it looks like. Oops. Sorry about that. Let me go in and run that again. Let's get rid of the z-axis so it doesn't get in our way. So we'll comment that out. Let's run this thing again. And notice, look at the masses here. The rock 1 is orange, and its mass is 80 billion. Rock 2 has mass 200. If you had to guess, which one of these objects do you think would move more in the real world? If you put them in space and start them from rest.
Rock 2.
Rock 2, it's so much smaller, right? So that's why we don't notice the code rock 1 is moving. But when I run this one, now the red arrow just means it hit saturation level. It still drew the arrow, but it didn't keep growing. What do you think? Is this constant acceleration kinematics? Could I use the equation delta x equals 1/2 at squared? And then again, v initial in this problem was 0, right? So could I just use this and then use a force equation, gm, whoa, that was kind of weird. Could I just use forces like the gravitational force to calculate the acceleration and spit this all out? What do you think? Is this kinematics equation valid?
It wouldn't be because both of the objects are moving.
And what happens if they move?
So,
To the acceleration.
well, it changes.
Yeah, in this case, do you think the acceleration is getting larger or smaller? Ignore the plus minus signs, because obviously it's going basically to the left. But is the magnitude of acceleration increasing or decreasing?
It's increasing.
Yeah, as they get closer, the force gets stronger, the acceleration increases. So how do you handle this in a code? Well, it turns out we do use constant acceleration kinematics in a weird way. What we do is we chop the problem up into tiny, tiny, tiny pieces. And for each piece, the acceleration is approximately constant. So this is what's weird. You would not do this on paper and pencil with kinematics, but because we're coding, it's easy. What do? First, you calculate where the rocks are currently located. You use that to update the force. As they move, you get a slightly different position, you get a slightly different number. All right. Then you calculate the rock's momentum. Finally, you use the rock's momentum to update the rock's position. And I should be careful. I update the rock's momentum. And then this is just cosmetic crap. Fine. And then you increment dt and you do it all over again. So these equations right here are constant acceleration kinematics. Now, this is not true if we use a large dt. Let's see what happens here if I set dt equals 0.5. Let's see what happens. The ball actually goes through here. This is a numerical artifact. What if I make the dt 1? Let's see. If I make this 1, by using too large of a time step, the computer code can have some trouble. Look at that. That's totally unrealistic. It went backwards. Did you see that? And so here, this requires us to pick a wise choice of dt. This is only valid if our dt is somewhat small. So probably right around here is maybe an upper limit. Sorry, one last time here. And clearly I put in my while loop break if the positions are inside each other, essentially. And you could study that in lab this week. Let's look at another variation on this one. All right, just for fun. Let's say we have this one. Can't remember what I've got here. Oh, so here's an orbit like this, right? Now notice in this case, it's not a circular orbit. You see that? What shape does that kind of look like to you?
An ellipse.
An ellipse. And notice the planet or the orange object is at one of the foci of the ellipse. So this is kind of cool. notice you could also see I'm plotting down here the radius as a function of time. So we see that sometimes the particle is about 5 meters from the center, and sometimes it's 10.5. And so that's kind of what we're seeing here as this thing moves around. But we could even do this one. Let me see if I've got this one. Let's say this one is let's say this one's moving that direction. Let's see what this looks like. Hopefully this is enough to actually make it do something. Oops. Oh, there you go. See that planet moving at the center very subtly? And so now this is started. You could imagine if one of the planets is moving, this will hopefully affect the orbit the next time. And so it doesn't exactly line up on itself. And then we could even go one step further and do it like this. We could stick in a Z component. Like this. And you could start running this thing in 3D by using the vector formation. So I'm going to get in here and we can look at this thing. And notice it's starting to curve out of the page and track it. And so we could actually do much more complicated problems in the coding if we learn how to use these R-hat vectors and stuff. So I hope this is kind of cool, giving you an idea of how these objects might move through space. And this is really the first chapter where you could be like, oh, I see. You can't do that stuff on paper and pencil very easily, where look how easy it is. You are going to do this in class and it will be easy for you based on what you've already learned. And you'll be like, oh, this is not nearly as hard as chapter 12 lab or chapter 11 lab or what the heck, chapter 10 lab. That was the one that got everybody. So I think what you will see is you can actually appreciate now there are certain problems it's much easier to code than it is to do paper and pencil. Paper and pencil will always have a place because you need to check your codes, right? So the easiest way to check this code is to see if it works in circular motion, punch in the numbers and see if you output a circle. Then you could be like, aha, my code's actually working. And that's one of the things you'll do this week. All right, so questions on that? Well, let me, before we start doing actual problems and grind through it. It's slightly interesting, and you could see, hopefully, there's a small benefit to the coding. Okay. Whoa, let's see here. Where do I want to go? All right. So, all right. Keep this page close and page 117. We're going to do the bottom problem first. Just keep it easy. Now, here's a couple of things I summarize about the energy. Here's a couple of things I summarize about the force. Let's just do the problem here. Let's do an actual problem now. And now a lot of you probably don't do the problems with me. This is one I want you to get out your calculator and actually make sure you know how to type these numbers in on your calculator. All right. Just trust me. Every once in a while, there's a student that screws it up and we can correct it now. Whereas if it's during the exam, it's too late. So let's make sure you know how to work with scientific notation because it's been a few months. All right. So I'm going to write some stuff down really quick. (13.1) mass of the Earth 5.97 times 10 to the 24th, I think, right? Let me check. Yep. Mass of the sun. Isn't that 1.99 million times, or a million? Yeah, a million times bigger, right? Wow, that's crazy. And then the center to center distance from Earth to Sun. Let me ask you something before we do this. Do you think the size of the sun in the real world and the size of the Earth in the real world matter compared to the center, to the distance between them? Do you think that matters at the 1% level? Do you think that would maybe affect the third sig fig? What's your gut tell you? Go ahead. What do you think? No, look at it. This one is on the order of, wait, where is it? The planet is about 1 million meters. The sun's radius is about 300 million meters, but the distance between them is 300 or is like 150 billion, right? So these other little radii are negligible. So this is not to scale, right? It basically looks like a fat dot, a tiny dot, and that's really more to scale, right? And even there, that's an exaggeration. They're even smaller than that. It's like, it's mind-boggling that you can even see the sun. It's so far away. Just, it's astronomical quantities. They're really wild to think about. All right. So let's not overdo it. Let's just make sure you can punch in the numbers right and see. Where's my black marker? Oh, there it is. It was in my hand. Sorry about that. So let's take a look. If I want the force magnitude, let me get my, get me up there. Okay. So we have problem 13.1. I want the force magnitude. Well, the force is G M1 M2 over radius 1,2 squared in the minus R 1,2 hat. But if I just want the magnitude, I just take off the hat vector and we just get the magnitude. Let's start simple. In this case, when I plug this in, 6.67 times 10 to the negative 11. That's why these gravitational forces end up being so small despite huge masses. It's like negative a billion almost. Times, and that's newtons times meters squared per kilogram squared times 5.97 times 10 to the 24th kilograms times that. I don't always work these out, but I do think it's worth it to do one of them all the way through, okay? First off, let's check the units and make sure they work out. All right. So in this case, oh, wait, what did I forget on the bottom?
Squared.
Squared. Now you know what you might mess up, right? So the meter squared is going to cancel those two. The kilogram is going to cancel the kilogram squared. I get units of newtons. That's a good thing. And then when you punch it in, maybe you've forgotten, maybe you remember, but just in case, the EE button is handy. So because we don't do a lot of scientific notation for the last few weeks, so right, you do 6.67 EE negative 11, right? And then you don't have to do the time. Oh, and now yours might be a 10 to the whatever. Just double check you know how to work your calculator. Let's do it. So finish the rest. I'll do it as well. Take the time to actually do it so you don't have to learn this during the test and be stressed out. And then I'm going to divide by, either remember your parens or just divide by it twice. Divide by 1.5 E11. Whoop, E. Wait a minute. This should be positive 11 right there. Do you see that? That should be 10 to the positive 11. The radius is large. to the sun, right? So that should be a positive 11. Sorry about that. So like what I'm doing, instead of squaring it, I'm just dividing by it twice like that. And so I got that. Whoops. About 3.53 or something, 3.52. Whoops. Yeah, something like that. Times 10 to the 22 newtons. Ten to the positive 22 newtons. All right. So far, so good. If you had to guess, let's look at the next part. I think it's the moon and the earth, right? Which one do you think exerts more force? The moon is a heck of a lot closer, but the sun is a heck of a lot bigger. Which one do you think exerts more force on the earth?
The moon.
Which object does the earth orbit? There you go.
The sun.
And so it ends up being the sun. Now, and so it's not obvious when you look at the numbers right away, but the trick is, look at the moon's mass, right? Where's the moon's mass? Where is it? Sun has, moon's mass is only 10 to the 22 kilograms, right? It's still 10 to the 6th meters away, but yeah, it's 10 to the 8th times the number of kilograms less or whatever. So when we run this one, let's take a look at it. Whoops, that's not where we want to go. All right. And so there's the numbers you get. So hopefully you could check that out. So which object affects the Earth's tides more? Do you know?
The moon?
The moon. So here's a question for you. The sun exerts a much larger force, about 100 times larger, yet the moon has a greater influence on the tides. Do you guys have any idea why? It's okay if you don't, but I'm curious if you have a guess.
Is it because the moon rotates around the Earth faster?
You know, that might be a factor that plays into it. That's not the dominant thing that I was thinking about, though. That's a good, that certainly relates to the tides. Absolutely. But what else?
Because it's closer.
Okay, what is it being closer due to it?
It's going to make so if we look at the gravitational force thing, the bottom, if it gets smaller, then it's the whole thing's going to get bigger, I guess.
Let me see if this helps. I'm just going to do a quick calculation here. Hold on. All right. So let's just punch in some constants. Let's forget about units. Let's say there's a mass 1. Let's just say it's 1.99 E. Let's just say it's 1 E6. And let's say mass 2 is equal to 1 E6. Sorry, I'm having sloppy formatting here. And so let's calculate, let's say the radius here, we can't start at 0 because the function will blow up, but let's maybe start at, say, 0.5, and we'll go by, and let's just plot this thing for a little bit, okay? All right, and let's get the force, and let's say it's equal to G, we're getting the force magnitude, that's a constant, times M1, that's a constant. Whoops. Sorry, I typed the wrong number there. F4 times the next mass. That's a constant. I accidentally got an extra multiply in there. Wait, what happened to my B2? All right, sorry. Okay, there we go. And then divide by, geez, I'm having trouble typing today. The radius, and we're going to square that. All right. And when I run this thing, we could see, oh, that scientific notation is ugly. So let's go up here. Just do this as a number. And let's plot this thing. All right, now this isn't perfect, but it starts to give you an idea here. Let's cap this thing at, that's fine. Let's just leave it like that. I want to point out something that you could see in this plot though. Notice, where is the plot changing most rapidly? Small radius or large radius? Where does it change most rapidly?
Small radius.
Small radius.
Yeah, so there's more change here. So there's a larger change in the force magnitude when you're at small radius. So imagine if here's the sun, here's the moon, here's the earth. We know that the force from the sun is going to be huge, but approximately constant because it's way out here on the plot. Whereas for the moon, you're much closer to it. So it's going to be much smaller, but it's going to change more over the size of the earth. And that is the dominant factor here, okay? Because the moon's force is less constant over the size scale of the earth, it will have a larger percentage effect on the moon, on the tides, excuse me. So, all right, so far so good. Basically, the sun's farther away. It's so big, it causes more force. But even though it causes more force, that value is approximately constant on both sides, at the North Pole, at the South Pole. It's almost exactly the same force everywhere. Not exactly, but close. Whereas the moon, the force from the moon on the Earth changes a lot between the North and the South Pole and the equator and all of the different places and the different sides. So it changes much more dramatically. Yeah, that's one factor. All right. Now, well, let's see. Is the moon, the center to center distance changes and the force changes a lot? Oh, well, I tell you what, since we're there, let me mention tides. Okay. So if you want to learn about tides, I put some comments back here. So I think it's interesting to learn about them. I am not an expert on tides, but I know enough to know that there's many factors. And I think it is the next page, page 125. Sorry it took me so long to get there. Now, you could see that I found the change in the gravitational force at points A, B, C, and D is a little bit different. And it's changing by somewhere about 5%. So the amount of force here is going to be the greatest. Here it's going to be the weakest. And up here it's somewhere in between. And the idea is because it's different at each spot on the Earth, that's one of the factors that contributes to the water sloshing around. Now, the other factors include, okay, so that's the most important one, right? And then somebody was talking about the Earth rotating about its Earth-Moon center of mass. Let's talk about that later. There's all kinds of, yeah, this is crazy. But if you want to learn more about it, I think that's a pretty good spot. I really liked what they did. Look at this. Isn't this crazy? Bay of Fundy. 50-foot tides. Isn't that crazy?
That is crazy.
Whereas in the Gulf of Mexico, sometimes you only get one tide. I'm telling you, let me sum up tides like this. It's no joke. Trying to understand the tides is no joke. Okay. So, all right. Enough said on tides. Let me go back here. Cool stuff, right? Check it out if you're into it. Not on the test, but it's cool to learn about the world. All right. So now let's look at this gravitational potential energy. I don't really want to do it, but I do want to point out you should punch in the numbers and make sure you get this right. So let's at least do one of them. Punch in the numbers right now. Just do it one time, even though you don't want to. Let's all do it. I'm going to do it too. Figure out the potential energy associated with the Earth and Sun. So I get a negative 6.67 E negative 11 times 5.97 E24 times, what was it? 1.99 E30. And then I got to divide by the correct radius, which is the distance between them. And that's a 1.5 E11. So I got negative 5.28 times 10 to the 33. Is that right? I think I might have typed in a wrong number.
I got the same thing.
Wow, that's crazy. That's huge, isn't it? Let me double check. Oh, that's what I got. So notice one of the things that I was hoping you would do is check that minus sign. Okay, see that minus sign sitting out front? Gravitational energies are negative. Now, at first, this might disturb you, right? You're like, energy should not be negative. However, I tried to stress this a lot when we were doing chapter 8. The value you assign to gravitational potential energy doesn't matter. The size of the change in you is what ends up being physically meaningful in any problem. For example, let's say I have a ball here, and let's say it's 1 meter above the ground, right? And let's say I say this is y equals 0. This value would then be y equals negative 1.0 meters, let's say. And you would say the gravitational energy here, if we were just using our old formula, mgh, would equal 0. And let's say it's a 1 kilogram ball, and let's say g is approximately equal to 10 meters per second squared. Down here, what would be the value of gravitational energy? Approximately.
Negative 10.
Negative 10. So we could see it's totally fine to have negative energies. That's the same thing as just saying, where's your coordinate system at, right? Now, in this case, if the ball falls down, delta U is negative. If you raise the ball up, delta U is positive. This is exactly the same, whether it's got a positive value here or a negative value there. The idea is you lose energy coming down, you gain energy coming up. Well, so far, so good. Let's look at our new energy equation. Our new energy equation says U is equal to negative G M1 M2 over R. Well, what does that look like? If this is the radius between two masses, and this is the potential energy, what value do you get for the energy if R is a tiny, tiny, tiny number? If R is equal to 0, what would you get?
Infinite.
Huge energy.
Negative infinity, right? Negative huge, because there's this negative sign right there, right? So it would start here. And then what if R becomes very large? If R goes to infinity, what do you get?
0.
0. So it looks like this. It's the opposite of the 1 over R function. Now, if you go up to a higher height, let's say you start out at height equals radius of 1 meter, and then go to height equals radius of 2 meters. Notice your change in energy is positive, even though the energy itself is negative. So again, if you start out close to a planet and then you go higher up, you go to a less negative energy. Have you guys seen this before in a chemistry class, perhaps? This is very similar to the energy levels of the hydrogen atom. The energy levels are negative 13.606 EV divided by N squared. It actually looks a lot like this, where I'm going to cheat and just be creative here. What happens is if you look at the energy levels of different atoms, whatever. You get these energy levels where there's one here, then there's one here, and then there's one here, and they start to get more closely spaced as you go up. And the idea here is if you absorb a photon, you go from a very negative energy to a less negative energy. You increase in energy, even though the energy levels themselves are negative. I think that's enough on that, but any questions? It's okay for energy to be negative because we care about changes in energy and rainbow unicorns. This is what else we care about. You got to have that. Okay. Okay, so that's covered. Hey man, you got to have rainbow unicorns to balance all that negative energy, brah. Oh my gosh. I'm so not Californian. It's ridiculous. I grew up in Illinois, people. All right. So, all right. Oh, let's get back to the question at hand. All right. So it's okay for potential energy to be negative. Don't freak out. Okay. You could do the same thing with the Earth and the moon. Here's question E. Read this. If we add up the previous two results, so let's say we calculated the energy associated with the Earth and the sun, and I add up the Earth and the moon, that should be the Earth with both of the other objects. But we don't get the total energy. What's up with that? If I add up the gravitational energy from the Earth and the sun and the Earth and the moon, why do I not get the total?
Wouldn't you need the moon to the sun?
Yes. We need all three pairs. So underline something right here. The potential energy equation is associated with a pair of masses. Okay. The way I think about this is if I wanted U total, there's a trick that I use. And I recommend you use it because it's just easy. What I first do is you have to get each pair. We'll start with the number 1. And let's say this is number 1. Let's say this is number 2, and this is number 3. It doesn't matter what, but I know that I need to pair 1 with 2. Then I check, is there another possible pair with number 1? 1 with 3. Have I done 1 with every other possible object? Yes. So now I go on. What's the next object I could pair up? 2. I write a 2. I've already handled 1 with 2, so I go on. Are there any other ones that I haven't handled? Aha, 2 with 3. Got it. Now that finishes that one. And then 3, I start 3 plus U3, except 3 has already been paired with everything, so I know I'm done. That is my trick for making sure I get the correct number of energy terms. Essentially, if you have 3 objects, there are 3 ways to pair it up. If you're a math freak, which I know some of you probably are, maybe you know about combinations. You're taking, 3 things, choose 2, and I forget which way you put the numbers. I forget if it's there or there, but n choose 2. So I think it's usually 3 is the total number of objects, and you're choosing 2 at a time. That equals 3 factorial over 2 factorial times the quantity 3 minus 2 factorial. And that gives you 6 over 2, which is 3. So if you care, that's cool. If not, whatever. If you know Pascal's triangle, that's great. All right. I'm going to pause here. What do you think? So far, so good?
It's pretty cool.
All right. Is the math, all right. Yeah, let's keep rolling and then we'll take a break in a minute. All right. Let's try and do one more before we take a break. Okay. Look at this one. This is starting to show us kind of some practical aspects of these. A lot of times people do not tell you the center to center distance. It's actually somewhat uncommon on the Earth. Usually we talk about your altitude. So here's a common thing. The distance here that we have been calling r, that's the distance between this mass center and this mass center, is actually oftentimes switched to the radius of the planet plus the altitude, h. So it's common to rewrite these things in terms of the altitude. That makes the equation look a little bit uglier. Now check this out. You guys know that mg is the force due to gravity up until this chapter. If I look at this one, we are saying that that's supposed to be g, big M, little m, all over r squared. If you look, shouldn't this garbage right here equal g if r is close to the radius of the planet? And that is true. So if you look at this, this is just an upgrade to our old version of mg. The issue is g now depends on altitude. As you go farther and farther above the planet, we expect g should what? Increase or decrease? Do you think gravity goes up or down as you go away from the planet? Down. Let's take a look at it. So I did this problem, and notice, I don't know if you remember in this problem, maybe you didn't see it, I'm using a 1 kilogram mass. So that means this, if I use a 1 kilogram mass, I hope you agree that the force, 1 kilogram times g, basically this force and g should be the same size number because I used a special 1 kilogram mass problem. Notice this, if you go up 100 kilometers in the air, that's like 60 miles above the surface, it's still almost exactly the same size. 200 kilometers, you're still approximately the same size. So this is a low Earth orbit. This would be a fairly decent altitude orbit. 500 kilometers, you still have most of the gravity associated with the planet. Almost, like 85% of it, right? A little bit more, 87%. Only when you go to extreme altitudes, like 20,000 kilometers, this isn't meters, this is kilometers now, then the gravity starts to be negligible. All right. So in picture form, it looks like this. So we could see that even for the first, I don't know, 1,000 kilometers, it doesn't change that much. All right. Okay. Now let me ask you this one really quick. Let's look at 13.3 really quick. Satellite orbits the Earth. Well, the Earth's gravity is weaker at the satellite's position. We just discussed this. At the altitude of 400 kilometers, it's still about 9 meters per second squared. What keeps the satellite up there? And then the question is, how should a physicist respond to that question? Because obviously kids always ask you, what keeps the satellite up there? What do you think a physicist would say to that question? Or what do you think a physicist should say? Is there something that keeps it up there?
I think it's angular momentum.
Okay, I would go with that. That's a decent answer. I was going to say nothing keeps it up there. It's falling towards the Earth. It just never hits. That's my style, right? It's trying to fall down. And then what happens is a second later, it fell, but it's also moving around the, right? The curvature of the Earth is such that as it falls, it never hits. There's a famous picture in some of these books where there'll be a mountain at the North Pole and someone will throw rocks. And the first one will go here and here. And if you throw it hard enough, it's just going to go all the way around the planet and hit you in the back of the head. Dope. So, right. And a ball, you don't think of a ball as being kept up there. You think of a ball as falling towards the earth. It's just this absurd limit where it's falling forever and it just never hits. So that's how a physicist probably thinks about it. And I think that's a better way than saying something keeps it up there. Now, you could argue, again, it has angular momentum. And so that's a reasonable thing. You're saying it's orbiting so fast it never hits. That's the same kind of thing. I'll give you it. All right. Any questions about that? Nothing keeps it up there. It's just falling and never hits. That's probably a good way to think about it. Let's look at this 13.3 really quick. Okay. I'm just going to make this jumbo. You got a satellite of mass m, little m. It's altitude h around a planet of radius r. And we're going to assume the mass of the planet is huge. So just like our simulations, the mass of the planet is huge. I'm going to draw the FBD over here. What is one force acting on the satellite as it orbits in this position?
Gravity.
Okay, which way does it point at that point in the orbit?
Towards the center of.
Okay, do you agree that's straight down?
Shouldn't
Okay.
it be like diagonal?
Isn't that straight towards the center?
Oh, okay. Sorry, I
For
was
the-
looking at the wrong place.
I'm looking for the instant shown here. Sorry about that.
Yeah.
Okay. So do you agree for this instant it's straight down?
Yes.
Okay. So what's another force acting on it as it orbits?
Force to the right.
What force is to the right?
Velocity.
Is velocity a force?
No.
So I'm not going to draw that.
Are you gonna say the fictitious force again or no?
Nope. This is it. Nice job. This is it. It's accelerating towards the center, right? That's it. Easiest FBD in the whole course. One force causes circular motion. Isn't that cool? One of the things, so I was trying to give you this hint where sometimes on test day, students overthink this circular orbit problem. There's one force towards the center and that's it. Cool. Now, in this case, the force due to gravity is G times M times big M over R squared. That's the magnitude. This should equal what? That's the net force. What does the net force equal for an FBD?
MA.
Which mass?
Well, if we're talking about the satellite, so small m.
Exactly. I drew an FBD of the small mass. This is the force of gravity on the small mass, right? That means I use the mass of the small mass right there. Nice job. Notice what drops out. And notice this is V squared over R. When I do that, do you agree that you could see the speed here? V and solve for some junk. I think it's V is going to be the square root of some junk. That's a technical term. We'll look it up in a minute, but do you kind of follow that? The speed should relate to the square root of some crap, where some crap is this stuff, this stuff, this stuff. One of these drops out, one of those, something like that. Okay. How would I get the kinetic energy of this satellite? What's an equation I could use?
1/2 mv squared.
Okay. It's a rotating body. Shouldn't I have to use 1/2 I omega squared?
would you need like both? So you'd have to add
No.
those two?
Either one is valid because the moment of inertia is going to be m times the radius squared. But notice r squared omega squared is going to give you back v squared. So if the object is a point mass, whoops, not zero, sheesh. If the object is a point mass, you could use either one of these two. That was something I alluded to in chapter 10 and 11. Because the satellite is so tiny compared to this thing, you could treat it as a point mass. And then the moment of inertia for the point mass reduces back to translational kinetic energy. So you could use either, but you don't use both. All right. Now, in this case, I want to talk about the potential energy as well. The potential energy would be negative G M M all over radius of the planet plus H. So keep in mind, anytime I have a little r, remember that little r here, is equal to capital R plus H. Notice in this chapter, you're going to have to pay attention to lowercase mass, lowercase radius, uppercase radius. This is very standard in many physics textbooks. So especially with your M's, I write a lowercase m like this and an uppercase M that's pointy. That's how I can keep track when I'm writing my notes, okay? Lowercase m is curvy, uppercase M is pointy, and then I could tell the difference when I'm tired in the middle of the night trying to get a problem set done, okay? Lowercase m is curvy, uppercase M is pointy. All right. Now, you may not see this, but give me just a second. I'm just going to rewrite this another way just so I don't have as much confusion. It's just negative GMM over R. Which term is bigger, the kinetic energy or the potential energy? What does your gut tell you?
Potential.
Okay. And do you know the value of the kinetic energy? Can you see what it would be? Let me give you a hint. Rather than solving for V, which is the square root of some junk, let's do this another way. Whoops. Give me a second here. I lost a squared. Let's just keep this rolling here. G M M over R squared should equal M V squared over R. Do you agree one of those radii cancels out? What could I do to this equation to very quickly compute the kinetic energy?
Divide it by 2.
Yeah, just divide both sides by 2 and look at this equation. Compare it to that equation. The kinetic energy is minus 1/2 of the potential energy. Notice this minus of that minus makes it positive. I know that seems crazy, but again, look at it. It's negative of a negative number, and it's half as big. All right. So should the total energy be positive or negative? Total energy, if you add the kinetic and the potential, should the total energy be positive or negative?
If you add, it should be negative.
Yes, and that's just like the orbit problem in chemistry. All right, so if we look at this one, let's scroll down here. Here's all the math. Notice total energy ends up being negative. It ends up being this weird thing. So we kind of talked about this. The kinetic energy ends up being negative 1/2 of this. Now, here's some phrasing. If you go to a higher orbit, I like to say the energy is less negative, right? If this number h becomes bigger, this entire fraction gets smaller. That means you're a smaller negative number. That's why I'm saying you get less negative. Here's another way to think about this. If the energy is 0, the planet is having no effect on you. If the energy is negative, you don't have enough energy to escape it and you're stuck in orbit. And I must have written this when all those banks were too big to fail. Okay, so yeah, anyways. So you could either say the energy becomes more positive or less negative as you go to higher orbits. All right. Questions on that? That's what I was trying to show right there. You go to a larger radius, you end up at a less negative number. All right. Let me show one more thing. What if you want your satellite to stay over Nipomo or Santa Maria all day, every day? What period would you want your satellite to have? If you want it to stay directly over one place and constantly be spying on my rainbow unicorn, what period would you need?
Would you want it the same as the Earth?
Yeah, 24 hours, right? And then if the satellite is orbiting one time every time the planet rotates, that's called geosynchronous orbit. If you want to, you could use this problem and figure out some neat stuff. So let me see here. Whoops, let's go to this one. I think it's right here. I did some plots here. Notice if you get to this special altitude of about, there it is, 335,900 kilometers, you end up with a period of 24 hours. So you can imagine that's a pretty cluttered area of space. Everybody wants that radius, right? So now I do want to stress to you, you don't have to make these plots. But I learned a ton when I wrote this book by having to make the plots, because I was like, oh, shoot, I got to convert this or that. There are little things that you learn in making the actual plots. If you've been making some all semester, these should be easy to make. And hopefully you can see if you get the same kind of stuff I do. It forces you to check your minus signs and your units. All right. All right. And I think, let me see if there's anything else I want to say before we take our break. All right. So please actually make these plots. All right. You learn something. Oh, this is a cool one too. Well, here's a neat one too. I don't know if you noticed this, but in those equations, if you look at those equations carefully, the speed of the satellite depended on which mass. Do you remember? Which mass canceled out when we were doing the force equation and which one survived?
The small mass.
The small mass cancels out and the big mass survives. So we see that the speed at which a moon goes around a planet will tell you about the mass of the planet. So if you're wondering if they put all the planets on a triple beam balance in chemistry class, no. You just time the orbits of planets around them. And from that, you should be able to compute the object's mass. Now you've got to know distance as well. So blah, 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 blah. It's not easy. But if you're wondering how you can get the mass of the moon, or I guess if you want the mass of the Earth, you see how long it takes to go around the sun and you get the mass of the sun. If you want the mass of the Earth, you get the moon going around the Earth, see how long it takes to go around, and then you get the mass of the Earth, et cetera, et cetera, et cetera. That's one way to do it. All right. Now let's take a break, come back in about 10 minutes. All right. So on my clock, I've got 5:50, basically 6. So let's come back at 6:10, 10 minutes. Oh, shoot. Oh. All right, almost time. Any questions? All right, so it's about time to get back. So, before I forget, I wanted to tell you something about Wednesday. Now, I know not everybody can come to the other lecture, but I believe I have guest speakers lined up for the Wednesday lecture that is at the earlier lecture. You're welcome to come to that if you can. I don't know what time they're going to be there. You know, I just kind of tell them and then cajole them and try and sucker them into showing up. And sometimes they forget, but they should be there. And I don't know what time they'll be there. So if you wanted to come to the Wednesday lecture, or if you prefer to not come to Wednesday evening lecture and just watch the live stream of the earlier one, that's cool. So I'll try and live stream the speakers, assuming they're willing. So one of them hopefully will be Chris Moon, that guy. He used to work at Agilent, and he now is, I forget, I think he's working for Apple. The other day he had to choose between 3 jobs they offered him, 2 at Apple and 1 at some self-driving car company. So he does all right. And yeah, he's doing all right. And then the other one is a friend of mine from grad school that he's now at Amazon in their quantum computing division. And so and he just transitioned from D-Wave, which is a different quantum computing company. So they have an interesting industry perspective on what it takes to be a physicist in industry versus a physics teacher, which is very different. But one thing I can say is they both got hired recently. So you might find it interesting to ask them questions about what is the job interview process like in the current market. And I think that would be useful to anyone, regardless of your major. Obviously, they're tech and computing and physics and all this stuff. But yeah, so just letting you know that's happening Wednesday, probably at the start of class. That's usually when I do it. But again, if they show up later, whatever. Okay, let's get back in, try and do a couple more problems. We got about a half hour. And let's start by looking at page 119. And I'll bring a screen share up. All right. So here we go. This page is a pretty good one to study for the final exam, right? It's got forces, it's got energy, it's got different types of geometry, it's got straight lines, it's got triangles, it's got squares. It's basically pretty good. It's got a number of different features here. All right. So, and I think the next page is pretty good too. Yeah, that's a pretty good one too. All right. 13.10, not so much, but all right. Let's try and really nail down the force aspect. So we'll probably do some potential energy calculations next time, but let's look at this one. We've got 3 masses at rest on top of a table. 1, 2, and 3 kilograms. The center to center distance is labeled there for each one. And the origin lies at the center of M3. So if you want, I used red and green, not the best color choice, I know, but I've also labeled them in the solution with letters. So in case you can't see that, that's fine. So, all right. Well, before you do any math, read these numbers carefully. Which mass, 2 or 1, exerts a larger force on 3? What do you think? Take a guess. It's okay to be wrong.
1.
1,
Why do you think 1?
Closer.
because M2 is at a diagonal. So
Yeah,
it'll be
so it's
like
farther away. However, why might someone think 2 could produce a larger force?
greater mass.
Greater mass. So it's not obvious, right? It's farther away, but it's also more mass. So would you give me this? Would you agree that they're probably about the same size? We don't know which one's larger. Maybe we think 1 is going to be a little bit larger, maybe 2, depending who you are, but they're probably kind of about the same size, right? So now, what direction is the net gravitational force? To figure that out, let's draw the forces on 3. So what direction is the force for that 1 exerts on 3?
From the center of mass up to M1.
Yeah. So that's the force of 1 on 3, right? Up. And then the other one is going along this line here, right? Sorry, that's so crappy. That's the force of 2 on 3. What direction is the net force on 3?
In between.
In between them. So you could also do the parallelogram rule, right? This isn't perfect. Pretty bad parallelogram. But you might think the net force is closer to the y-axis than the x. Now, don't overthink this step. The idea for me to include this is when you are doing problems, you can use this logic to check your work, but it's not a perfect check. We don't know the answer. We just know it's probably closer to the y than the x. So if I was doing all of this and I could use this to check my answer at the end, I would expect the angle to the y-axis to be small or the angle to the x-axis to be large. Said another way, I expect the I hat component to be negative and small and the j hat component to be positive and large. That's all that's good for. That's it. You could check your work with a picture. Enough said. So I'm going to show you 2 ways to go ahead and do this calculation. And I'm going to cheat and go to the solutions because it's neatly written up already. Now, so it turns out 2 is actually slightly larger. Isn't that crazy? Look at the numbers. So it's only 20% farther away, but it's got twice as much mass, 20% squared, blah, blah, blah. It's, yeah, okay, whatever. Okay, so you could do the actual numbers and run them. It turns out 2 actually produces more force than 1. That said, what I did here was I calculated the magnitudes. Again, I used G M1 M3 over R13 squared. Now, I then took the vector components for number 1. Number 1, I see it's none in the I hat and all in the J hat. For number 2, what did I do? Rather than solving for theta, I solved for cosine theta and sine of theta. So I used this triangle right here. And rather than getting the angle as being 53.1 degrees, I just got the sines and the cosines of them. From there, I punch in those numbers. I add up the i's with the i's, the j's with the j's. And we got this thing going. So that's style 1. We're going to go through style 2 in just a minute. What do you think of style 1? Does that make sense to you? Okay. All right. So now I'm going to clear out my annotations there. At first, you're probably really liking style 1 because it feels very much like chapter 3. However, if you ever want to handle problems in 3 dimensions or coding or anything other than the most basic problems, we actually require style 2, right? You have to learn how to write problems with the hat vectors. Now, at first, this is going to seem confusing. Just trust me, it is worth the effort, especially because I know who's teaching Physics 163, and I know which style is most useful in Physics 163. I wonder which style it is. I just don't know, or maybe I don't know. Maybe style 2 is useful. So let's just trust me and fight through it. So here I got the magnitude, but instead of trying to write sines and cosines, I write it as a hat vector. Now remember, this is equal to R 1 to 3 vector divided by R 1 to 3 magnitude. Now at first it seems very confusing. Look at this. I'm getting a negative J hat. But remember, when you plug it in, the definition of the force is negative of the R hat. So this happens all the time, and it's very frustrating for students at first. You're like, this doesn't look right. Shouldn't it be positive J hat? You got negative J hat. But negative of negative J hat is positive J hat. This works. Similarly, when you look at the unit vector 2 to 3, it's going from 2 to 3. So notice it's positive 30 in the I hat, negative 40 in the J hat. When you plug it in, the sign gets flipped. This same thing happens in electricity where you have positive and negative charges. The same kind of thing happens all the time. So by writing these equations this way, they will look exactly the same as our electricity equations later. That's why I'm trying to show you this, okay? And if you try to code it, this is the kind of junk that makes sense in a code. This would be a real pain in the ass in a code, right? You do not want to do all that work that you had to do with chapter 12 every single time, or sorry, chapter 10. It's nice to just use the ball's position and minus another ball's position to get these vectors and slap a minus sign on it. All right, there's our picture. I'm looking at this picture down in the bottom right corner here. Sorry, let me circle it. That's the net force, which is kind of what we thought. Now, the most common mistake I've seen that drives me nuts is students try to put x squared on the I hat and y squared on the J hat. That doesn't work. The key here is you get the magnitude using the R vector, right? If you always get G, M over R squared. You don't use just the X, you don't use just the Y, you use both of them. And then you split it into I hats and J hats in one of these two ways. In both of these, you get the entire force magnitude using R, then split into components. That's the one thing I want to make sure I stress. Okay, questions? Okay. Now look at this. It turns out the Earth itself is exerting a 30 Newton force on M3, right? M3 times G. M3 is about 3. G is about 10. That's about 30. Look at this force. 3 nanonewtons. That means if I could draw this up here, give me a second. On this original one, right, we know that we're looking at a top view. So there's a normal force coming out of the page, and there's M3G going into the page. And both of these are essentially 30 newtons. we also know because this mass is attracted to the other objects, there's this tiny little force this way of 3 nanonewtons. All right. Now, I hope you agree, even the smallest of frictional coefficients is going to easily balance that out and keep this mass from sliding across the table and bumping into the other masses. If you put a bunch of pool balls on a table, they sit there at rest. They don't start creeping towards each other due to gravity, right? Now, that doesn't mean we can't use this to our advantage. In particular, the next time you go out to the club, if you want to feel attractive, just think about the gravitational force. You're constantly attracting everything else in the room, the spoons, the other people. You're always attractive with gravitational force. It's just so small, it doesn't really help much. But you are always attractive. Brutal. Brutal. Yeah, look, I'm attracting that unicorn, right? But it's not drifting towards me. The masses involved are so small that the magnitudes are, that's probably even smaller than nanonewtons, right? So, all right, whatever. So these forces are tiny. That's enough said. What do we got? 20 more minutes? Why don't we just stop here for the semester, give everybody an A and quit? No, oh, wait, never mind. I guess we'll do another problem instead. Wouldn't that be nice? That's what I want to do. So broken right now. Let's get through it, fight through it. Okay. Ooh, here's a good one. This one is deceptive. When I first wrote this problem, I said, this is a one-dimensional problem. It's really easy. All I have to do is just plot this thing. And I figured out the force. Turns out it was non-trivial because this is complicated now. If I'm sitting over here, both forces point to the left. If I'm sitting here, I get one to the right and one to the left. Whereas if I'm over here, both forces point to the right. And at first you may say, this isn't too bad. But this is one of those ones where I tried to plot it and discovered this is not easy to work out unless you do style 2. So if you take a problem that looks like you don't need these vectors and we punch it in with vectors, let me show you here. Because this X value could take on many different numbers, right? There's 3 regions you have to think about. And you have to make sure your answers work out for all 3 regions. So when you do this one, you get all these complicated looking formulas. Now, does it still work? And you have to think all this through. And oh my gosh, it's really ugly, blah, 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 blah. And I got this result. And I discovered, what if we just do this thing with hat vectors? And I wrote this all out. If I use the hat vectors, for me, the problem made a lot more sense. I was able to get these equations for the hat vectors more intuitively. So sometimes, I'm going to let you work through this one later, sometimes even these seemingly simple one-dimensional problems can benefit from using the full vector form of the force. That was the point that I wanted to make. Now, that's a tough problem, but I'm going to let you kind of look at it. Another trick here, this is wild. You could first calculate the potential energy. How do you get from potential energy to force? Do you remember? How does one calculate force from potential energy? Let me give you a hint. What if I had a plot here of U versus X?
And potential is 0?
What's that?
When you when the potential energy is 0. So when it crosses the x-axis.
What about that point?
That's the maximum, or that's the lowest potential goes, so that's the maximum force.
That's not good reasoning, it turns out. You're on the right track though. We got to be, this is what I'm looking for in general. How do you get the force at any one point? How would I get the force right here? Or how would I get the force at this value of X or the force at this value of X? Do you remember what we did to get the force at any one point on the graph?
Negative work? No. Slope?
Negative slope. Remember that? So, and I think that's what Alonzo was alluding to. But basically, it's negative du dx. So in these problems, this is actually an even easier way. You correctly write the potential energy and then take negative the derivative of it. And then you don't have to work so hard to figure out the force. What? I'm telling you, you will learn a lot if you try to make this plot. All right. All right. So just be aware. Sometimes problems get nasty. To be honest, on the final exam, I wouldn't make you do all three regions of space. I would probably just say like one version, I would stick it here, another version here, and another version over there. But, you know, this problem shows the merits of learning how to do things the right way. And that's what I wanted to point out. So again, I'm not going to make you do all three regions on your final exam. I figure if you could do one, you could do the rest. But you can learn a lot from this problem, especially if you actually make the plots. It's surprisingly, you have to really know what you are doing to make a plot. Now, this is a good problem. So what we're seeing here is we've got like a rectangular geometry, we've got a linear geometry, everything on the line. Here's a triangular geometry, and then I want to finish with this square geometry. All right. So let's take a look at this one. Suppose we have 4 identical masses held in place on the corner of a square. Assume each mass is m. My bad, I didn't write that. So, all right. I'm going to write this on the whiteboard. Give me a sec. This is 13.8. Last one of the night, I think. Okay. Oops, let me get me up here. Okay, so we've got this situation right here. We've got 1, 2, 3, 4. And we want to get the net force on this 4th mass down here. What's the first thing that we might do? Anybody?
We draw the forces.
Okay. What direction is the force that 3 exerts on 4? What direction is the force on 4 from mass 3?
To the left.
Okay.
So it's F of 3 on 4.
Yep. And I'm just going to call it F34 because I'm lazy. Now, how about mass 2?
Straight
Yeah.
up.
Do you think it's bigger or smaller than this F34?
Should be the same.
Okay. By symmetry, it's the same. That could be useful later, right? Notice if I can calculate one of these magnitudes, I've got the other one. That's the kind of stuff you could do to save yourself some effort. Okay. How about 1 on 4?
Splits the 2.
Okay. Should it be bigger or smaller or same size? What do you think?
A little bit smaller.
Yeah, it's the same mass. It's more distance. It's going to be about half the size. You might say, how do I know it's half the size? Well, how much bigger is the radius? What's the radius up here to this one?
The square root of those 2 sides.
So look, if I square that, the square root of 2s is 2s squared. So I know in the denominator of the force equation, I'll get s squared for this one and 2s squared for this one. So this one should be half the size. So if you could see all this, look at how much easier this problem becomes. You're like, hey, I'm going to calculate this magnitude. I'll divide it by 2 to get that one. And I know I've already got that one. And then it's much easier to do, split this one up, SOHCAHTOA 45 degrees. Another thing you could do is this. Do you agree that the force on 4 in the x direction should basically be the size of F34 times -1, meaning negative I hat, plus the size of force 1,4, that's force 1,4, cosine of 45 in the -1 direction. Again, this is like the I hat and this is like negative I hat and negative I hat. So what you could do is first figure out the force on 4 in the x direction, then by symmetry, meaning a symmetrical problem, we know the equivalent force in the y direction should have the same size but be positive. What do you think about that? And again, these are just like your G, M1, M3, both of those are M, all over, in this case, S squared. Whoops. This would be M, this would be M, this would be S squared. You plug it in, you're good to go. The moral of this problem was to be, hey, sometimes if we think about it, we could save ourselves all the nitty-gritty details. You could save yourself some time by doing that. All right. Oh, let's see. Is there one more we could squeeze in? Let's do it. Oh, that's part A. So in theory, I think you could do that. Let's maybe take a look and see what I got there. Those are cool plots, aren't they? Okay, there's the triangle one. Okay. So depending how you want to write these out, the tricky one is that force of 1 on 4. Notice you get the 2, and then you have to remember to split it into I hats and J hats correctly. Right? It's not negative I hat minus J hat because these numbers are coming from cosine 45 and sine of 45. So you get a 1 over root 2. It's not negative I hat. All right. Okay. So the net force ends up being this weirdo number. That's cool. Now, let's go to part 2. Let's say I want to get the gravitational potential energy. How many terms am I going to get? What's the first potential energy I might write down?
Six?
There's going to be 6 terms. How could I make sure I get all 6? What's the first one you might write down?
1 on 4.
Okay, 1 on 4. Then what?
2 on 4. Oh, sorry.
Okay.
Sorry. 1 on 3 then, I guess. Let's start on 1 on 2 then first.
Yes, there you go. And so the trick is, it's not that you can't figure it out. It's let's just do it the same way every time. 1 plus 2, 1 plus 3, 1 plus 4. I'm done with 1. Next, Jesse, what would be next then?
2 on 3.
2 plus 3. And then 2 plus 4. I've taken care of the 2's. Next, I go to 3. 3 plus 4. And now I'm not double counting. That's how I remember it. And you'll always see you lose 1 each time through, right? So, okay, whatever. There's going to be 6 terms. Question. Which of these 6 terms are going to be of the same size? Are there any others that are the same size as 1, 2?
1, 3.
1, 3. I agree. Any others?
2, 4, and 3, 4.
2, 4, and 3, 4. So even though it looks ugly, you could basically figure out one of these and multiply by 4 to save yourself some effort. And then what do you know about 1, 4, and 2, 3? I think those should be the same as well, right?
Yes.
So the idea is, even though it looks like it's going to be a ton of work, a lot of these end up being pretty simple. There's tricks in a lot of these problems to save yourself some effort. And that's where the practice pays off. During the final exam, when you don't want to spend a lot of time on this problem, if you've practiced chapter 13 enough, you know the tricks, you're faster, you get it done. All right. So, and then what's one thing that people often forget when writing down the potential energy? Remind me, what's the most common thing people forget?
It's not R squared at the bottom, it's just R.
It's R on the bottom. What's the other thing?
The negative.
The negative. Those 2 things. If you could remember that, these problems are easy. Okay. Now, wait a second. Let's figure this out. Okay, so let's read some of the rest of this one. If you wanted to figure out the net force on 4 when it gets to the center of the square, could we still use part A, or is it going to be different? If I release it, let's say I pin the other ones in place. So 1, 2, and 3 are held in place. This one's released from rest. I hope you agree it's going to start moving towards the center. And at some point, it's going to be exactly in the center. Is that the same force problem as before, or do we have to recalculate?
Recalculate.
Okay. Now, in this case, why is this actually not that bad to recalculate?
Isn't it just divided by 2 for most of it?
That I don't know. I don't think that's true. This one is closer, right? So that force should get bigger. What happens to the force from 3 on 4? It's going to be the same size. Agreed? However, what do you notice here about the forces going towards 2 and going towards 3?
They're the same as 1.
They drop out, they cancel, and they're the same as 1. So here's a case where you could ignore these 2 forces entirely if you're at the center, and then it's basically just do one force calculation really quick. And you could say it's twice as close, so it's 4 times bigger than what it was before. And I think that's what you were talking about, right, Jess?
Yeah, I was going something along the lines of that.
And so that would be true as long as you also remember the other components happen to drop out. So it would be 4 times the gravitational force of 1 from the first part. So you don't actually have to redo anything. Isn't that cool? Okay. I have a strange vision of what cool is. What do you think? Do you think gravitational energy is going to increase or decrease as it moves to the center?
Decrease.
Okay, why do you kind of say decrease? What was your logic?
More potential energy drops out.
Okay, yeah. It's going to be moving. So you've added kinetic energy. You must lose potential. So based off that, do you think it becomes more negative or more positive? The gravitational potential energy, will it become a bigger negative number or a more positive number?
Should become more positive.
More negative. You started out at, say, negative 10. And then let's say we go down here and we end up at negative 12. I'm making these numbers up. These are not real, but they are approximately like what one might expect. So if you go from negative 10 to negative 12, okay, let's say initially when it was in the corners, it was negative 10, and then you go to negative 12, what's delta U?
-2.
Negative 2 joules. So what is the change in kinetic energy? If you lost 2 from potential, what's going to happen to your kinetic?
Oh, you gain 2.
You gain 2. And that's just a fancy way of saying this is a conservative energy problem. I know that delta K plus delta U is the total change in energy. Well, if energy is conserved, what's the total change in energy? 0. And that tells me that delta K, the change in kinetic energy, is equal in size, but opposite in sign to the change in potential energy. So if you lose potential energy by going to a more negative number, you gain kinetic energy. It started from rest and moved that way. It must have gained kinetic energy and lost potential energy. Is that cool? Is that making some sense conceptually why the numbers become weird like that? Hope so. Okay. So, all right. Did gravity do positive or negative work as mass 4 is moved to the center of the square? What was the change in potential energy? Was it positive or negative?
It was negative.
Negative. How do we define work in a physics class? It's equal to minus the change in potential energy. So the work done is greater than 0. Think about it like this. When this mass goes towards the center, that's equivalent to a box falling towards Earth, right? This is falling together. It's getting closer to the other masses on average. So this picture like this is equivalent to that picture down there. When you fall down, gravity does positive work. Your change in potential energy is negative. It's the same thing. When masses come together, they lose, let me rephrase. They lose gravitational energy, or it becomes more negative, and you gain kinetic energy. All right. How would you get the speed of mass 4? We're almost done. Just hang in there. I promise I'll be done in 2 minutes. Determine the speed. What type of problem do you think that is? You want to get speed.
Energy problem?
You do an energy problem, right? Why don't you just do forces and then kinematics? Would that work?
The acceleration changes.
Exactly, because the force changes, the acceleration changes. What's another way you could do this if you had a lot of time?
You probably code it.
You bet your ass. So this would probably be the easiest way to do it, right? So you could literally set this problem up in a code. You put in 4 rocks, make sure some of them are fixed at rest. So you'd set the momentum of two of them to 0, and you basically only update the force on rock 4, let it rock, and you could get this calculation done to arbitrary precision. Whoops. All right, so let's stop that. Stop the live share. Stop everything.